I'm Ray.
And I'm Brian.
Yeah, and you know, this is Two Skis Walk Into a R.
Regression edition.
Yeah, it's time to regress. And stop squeaking my chair so everybody can hear what we're talking about. So in our previous videos, we've been doing ANOVAs where we had a qualitative predictor and a quantitative response. This time we're going to do regression, which requires a quantitative predictor and a quantitative response, both quantitative. And so this time we're going to do the pedal width and the pedal length of our friend the iris.
So what are we looking at? What are we trying to do with a linear regression? I
don't know, Brian. What are we trying to do? Get a passing grade?
Well, we love passing grades. We like education.
Yeah.
So understanding our natural world with data. But we're also trying to find if there is a relationship between the two variables, our quantitative variables. So we're trying to see, does a relationship exist or does it not?
Correct. Yeah, right. I'm glad you clarified that. So here we are. This is the data set, and you can download that data set here, tinyurl.com/envs-iris data with camel case. And so I went ahead and, did the file download as CSV, got that onto my machine, and then I did the the business in the console here. I did file.choose and then chose my file, put that file path right here. Always good form to put strings as factors equals true right there in that.
Absolutely.
And then check the structure of it. So boom, there it is. Let's make sure. Oh yeah, that looks pretty much like our data set. And then the structure. Oh yeah, we got numbers, and then a factor. It looks real nice.
Great. Okay, so it shows up in our environment and it shows up in our console when we run the structure.
Environment
STR.
and STR. Yep. Okay. So here we go. A regression of petal width versus petal length. That's the word. That's the word. Okay, and I'm going to turn this into a section with 4 equal signs. And now let's go to our regression workflow. So here we are. Step 1, establish the null and alternative hypotheses for the scientific question. This gets back to that purpose kind of that you were talking about a moment ago, Brian. And so our null hypothesis is there is no relationship, i.e. zero slope, between pedal length and width at the population level. That makes it a little easier for me to understand, at least, that we're talking about. The hypotheses are about the population, not about the sample. Okay, and then the alternative hypothesis is there is a relationship, i.e. non-zero slope, between petal length and width at the population level.
So what is this zero slope versus non-zero slope business?
Well,
am I derailing the conversation?
Yeah, maybe. I don't know. Like, if I could call that up quickly, I would, but I just can't. Yeah, if there's no slope between it, that means that for any change in the predictor, there's no change in the response.
Yes.
If there is a slope, then when you change the predictor, you're changing the response.
Yep. So as we think about the x-axis.
Yes, the horizontal axis.
That horizontal axis, as that x-axis value is increasing.
Yep.
There is no change to the y with the line that we're drawing.
Yep.
So basically, there is no relationship.
Yeah.
So with the x-axis increasing, where there is going to be a non-zero slope, it can either increase the y value as x increases, or decrease the y value as x increases. We'll show some graphs here, and we'll hit that home.
I just can't wait. Okay, so here we go with step 2. I thought someone was shoving something under the door, but they're not. It's just Kevin Erickson walking past, doing stuff. Anyway, so step 2. I feel like we're getting derailed. We're getting a little loopy making all these videos. So plot response predictor. That's pretty easy. So here we go. Plot. So visualize data. That's what we're actually doing. Great. So plot of iris.df $ petal width tilde iris.df $ petal length, and boom, run that guy. Whoa! I think that there
might be a relationship.
I think there might be a relationship. It seems that when you increase petal length, you're also increasing petal width.
Yep.
You know, not a huge surprise if you've ever looked at a flower or multiple flowers or flowers that are small and big. But here we are. It's good learning tool. So that's step 2. We have visualized our data. Step 3 is to create our statistical object. Again, LM now is our function that's going to create that linear model. And we again have to include this NA action equals NA dot exclude. Okay, so step 3, create stat object. Okay. So I'm going to call it M. You could call this anything you want. You could call this tables. You could call this microphone. You could call this Brian Osowski.
Good luck spelling it.
Good luck spelling it, but I'm going to just go ahead and do M. So iris.df $ petal. What are we doing? Width. Yeah, petal width. I could have just copy pasted, but iris.df $ petal length, okay, and then na.action equals na.exclude, and then I'm going to run that guy. Okay, so now I've created my statistical object. It's sitting there in the environment.
Excellent.
And now, that's fun. So now get the regression output. Determine their support for the alternative hypothesis. It's kind of fun. I think there's going to be, oop, that's not a pound. This is step 4. Get output. Summary of M, and this is the p-value that we care about. This is the slope of the line that you can imagine here. And so what this is saying is your odds of getting data like this, assuming that at the population level there's actually no relationship, is super deep. It's just the tiniest number that R can possibly produce for us. So definitely have support for the alternative hypothesis that there is a relationship.
So a non-zero slope.
It's a this looks like a non-zero slope to me. So that's fun. And then we can add a regression line to our plot right here. And so I'm going to actually do that up here in step 2. That's a little confusing because then I haven't created the
model yet.
Yeah, I haven't created the model. So I'm going to go ahead and do it here. So step 5, add regression line. And so that's going to be AB line, and then I just feed it that statistical object, and it should slap a line right up on top of there. Yep. So there's my regression line, as you would have expected. Okay, so that's all well and good, and that says a lot. That's we've learned a lot of things, but that p-value, we have not yet verified that it's valid. Like it could be an invalid p-value.
Absolutely.
In which case we might have to do this transformation stuff and yada yada. So let's go ahead and do this. Fortunately, at least one of these is, I mean, they're the same assumptions for ANOVA, and they're just a slight difference in how you do the homoscedastic one. But otherwise, all this stuff kind of transfers from your ANOVA knowledge. So let's do step 6A. Verify that the residuals are normally distributed.
Absolutely.
Okay, and it doesn't say to do it, but I do like to make a histogram of the residuals. I probably should add that to the thing. Residuals of M. Run that.
That looks pretty normal to me.
Looks pretty normal to me too. Let's do a QQ norm. Residuals of M, and then we'll do a QQ line. Residuals of M.
Also looks pretty normal.
That's pretty good to me.
The histogram and the QQ norm generally agree.
Yeah, generally agree. Yeah, you're looking. It's two different ways of looking at the same thing. And then we're going to do the Shapiro-Wilk test. And again, here's the Shapiro-Wilk. We kind of want data to be drawn from a normal distribution. That meets the assumption. And this is our cutoff, 0.001. So let's do that. Shapiro test residuals of M. And I'm going to include our H0. Our null hypothesis is data.
Good thorough coding, Ray.
Thank you very much. Data are normal. We'll just say that to keep it short. And that's going to be if we're going to conclude that if the p-value is less than greater than 0.001. And the alternative hypothesis is that the data are not normal. And we'll conclude that if the p-value is less than 0.001. Okay, so here we go. Oh my goodness, there's our p-value. It's like basically 0.09, which is definitely greater than 0.001. So this says that the data are normal, which...
So 6A residuals appear to be normal.
Great, wonderful, wonderful. Let's do step 6B. Verify that the residuals are homoscedastic, which means equal variance. And we can visualize that with a residuals versus fitted plot. So plot residuals of M tilde fitted of M. Let's run that. Oh, that looks a little heteroscedastic to me. I sort of see a flaring out here, like the variance over here when the values are small is smaller than when the values are large. So I see this kind of cone shape that's a
I always called it a flugelhorn.
What's a flugelhorn?
Google it, kids.
Oh, okay. All right. Okay, so let's
gotta have fun here at Two Skis.
Yeah. It's the height of fun. Okay, so now we're going to use an NCV test. This is in the car package. Oh, yeah, Brian's over here Googling a flugelhorn. Okay.
It's true, though.
It's...
Not trying to derail you, Ray. Keep going.
All right, I'm staying on task. Okay, so this requires the car package, so I'm going to go up to the top of my script. And I already did the business where I installed the car package, so I just have to get it into working memory. So that's library car. That's the one. Run it, and then I'll have all of that car stuff. You sometimes see this red lettering that looks concerning. This is okay. This is just telling us that there's another package, FSA, that I already had loaded, and there's a little conflict. But in my experience, students have never run into trouble with this kind of stuff. This is like if you're deep in the weeds doing some extreme coding that these kinds of things could ever really cause a problem. So I'm not worried about it. Okay, so now we're going to do NCV test. Which one is it? Dot test or... Oh, this says depreciated. Yeah, this one's depreciated, so let's do this one. This looks better. See how the little hider thing says these functions were depreciated in 2009. So let's use the one that's not depreciated. Because I prefer to appreciate things.
I appreciate, not depreciate.
Yeah. And so looking at the syntax, this is my statistical object, comma, NA action equals NA dot exclude. Action equals NA dot exclude. And our cutoff here is the same as for the Bartlett test. So we are kind of, quote unquote, hoping that it's going to be greater than 0.01 because that would mean that the variance is constant. It's homoscedastic. But as Brian and I sort of judged with our eyes, am I missing something?
Oh, we should be writing out our hypotheses.
Oh, yeah, writing out our hypotheses. He was pointing at the screen like, Ray, you're screwing it up. Okay, so the H0 is data are homoscedastic. P greater than 0.01. And then the alternative is going to be that the data are heteroscedastic. And we'll conclude that if P is less than 0.01. Cool.
Excellent.
Okay, let's run that. Oh no, this is a very small number. This is 1.39 times 10 to the minus 9th. So that's teeny tiny. That's telling us that Brian's famous flugelhorn is in effect. Okay, so what happens? So we did not, our p-value is not valid, so we have to try a transformation. And I'm going to just go ahead and try a square root transformation. And that happens right there in where you create that statistical object. So I'm going to go to step 3.
So Ray, we have 2 continuous variables.
We do. You're right. So which one am I going to square root?
Oh, I'm pretty torn.
Yeah, Brian's torn. Yeah. So I typically will start with the response, but that's just kind of shooting in the dark. Do you have something wiser to say than that?
No.
No? Shoot. Okay. Darn.
Oftentimes, I also do start with the response.
Yeah.
And if it seems that it has improved the data in terms of meeting the assumptions, you can also then either increase the strength of the transformation. A log transformation is a stronger transformation.
Yeah.
Or you could also transform the other variable, the independent variable, the x.
Because you'll see here it says you could do the response or you could do the predictor. Pretty cool. So let's try the response.
I'm going
to do a square root, and I could do SQRT, but I prefer to do it by raising it to the 0.5 power.
Raise Ray.
Come on, raise it. There, caret 0.5. Okay, so we're going to run that, and then because I've overwritten my statistical object, it's in there now. I can just run all of this other stuff. So let's see. Are we still? That's still kind of. It's a little less normal than it used to be, but it's definitely passing.
Yep.
It's definitely greater than 0.001, so we're going to conclude that that's normal enough. And now that looks pretty homoscedastic to me, I got to say.
Visualization is improving it.
Oh, and there we go. No problem. So we have passed both of our tests. Okay, fantastic.
So no need to over-transform all of the variables. We just kind of work through it in a piecemeal and logical way.
Yes, yes. So that now tells us that, if we go back to our raw data graph, which is, there it is, that this is statistically significant. But now watch this, folks. I'm going to do something funky. So we can replot our data, right? And now if I create this statistical object again, it's going to have that square root transformation in it, right? And so I can check, okay, it's still statistically significant, very statistically significant. But now watch, when I add my AB line, something funky is going to happen. It's not fitting well.
It doesn't fit.
No. And that's because I have this AB line is using my statistical object, which has the transformation in it. So probably the cool thing to do would be to plot the transform data as well. So let's go ahead and do that. So now I'm going to plot my transform data. I'm going to create my statistical object, and now my AB line fits beautifully.
Like a best fit line, if you will.
Like a best fit line, which is what it's called. And, we could also talk we got a couple. So that's basically the analysis, right? And so one additional thing to note is that in this context, we often talk about the R squared value. And I don't know if you have a strong opinion about the multiple R squared or the adjusted R squared. They tend to give the same information.
They're approximately similar.
Yeah. Often. So this is saying that basically 94% of the variation in petal width is explained by changes in petal length, which is a lot. So not a huge surprise. Bigger length petals are also wider. This is the point. So this is a teaching
biologically
tool.
Intuitive.
Yeah, biologically intuitive, the point of it all. That's kind of what that's saying. And there's a really strong relationship there, which again, is if you've ever looked at flowers in your life, you probably already knew that. But it's good to see the statistics confirmed with something that you're already familiar with. So that's what the R squared value means. And then do you want to talk about this additional issue?
I think we should.
Okay, so if you are feeling like you are
comfortable,
or rather, if you're at your limit, then stop right now. If you're totally comfortable with all this stuff, we're going to give you an additional statistical insight. This is like level 2 statistics.
Absolutely.
Right.
So when we're thinking about these statistical models, if we reflect back on our ANOVAs, we structured our ANOVA with a dependent response variable, our y.
Yeah. Hey, maybe I'm going to pull that up real quick.
That sounds great.
So I'm going to hit save here, and then we're going to pull up the ANOVA, this guy. That's the same thing. And then we're going to visualize.
Visualize that data.
There we go.
Excellent.
Yep.
So our dependent response variable in this case will be sepal width, see video number 1.
Yeah, video number 1.
For
right.
understanding an ANOVA. And our X, our independent, is going to be categorical. In this case, species.
Yep.
So we can't actually put a numerical value on these different species because they are going to be Setosa, versicolor, and virginica, but we can't mathematically arrange them along a continuous scale.
I'll agree with that.
So what we're going to do is this is going to be very clearly our independent variable.
Yes.
How does sepal width vary across these 3 species?
Yep.
So when we go back to our linear model, we still have this same concept of the dependent response variable on the y-axis, and then the x is if we have an independent variable, we would put that onto our x.
Yep.
And so an example might be if we added a range of nitrogen, increasing nitrogen,
yep.
and we experimentally designed it where we're putting in known amounts of nitrogen.
Did you know I've done this very experiment?
I know you did. This is right to Ray's heart. And then we look at, say, the growth of the plants with increasing nitrogen. The growth of those plants are very obviously dependent upon those rates of nitrogen.
Yes, and we know what those rates of nitrogen were because we cooked up the experiment. We cooked up the experiment. We mixed up the fertilizer like right there in the lab across the hall, all of it.
Absolutely.
Yep.
And so
they're known without error, you could almost say.
It's known without error. So that is a independent variable.
Yep.
But here, we also have the power of determining the relationship between variables.
Yep.
And in this case, when we are looking at petal length versus petal width, there is no real true, how do we know
which one's independent, which one's
independent, which one's not.
It's the totally different scenario.
It's a different scenario. But in this particular case, we don't have to overly concern ourselves with which one is going to be which, because we're trying to detect a relationship between these two, which we are projecting or at least questioning of an increase in plant width, petal width would be also an increase in petal length.
Yep.
But we just have to be very careful when we have a known experiment where we actually are going to be laying out the details of a known quantity, in the previous example, nitrogen.
Yep.
That has to be on the x-axis.
Has to be on the x-axis. Another way of saying this is the regression analysis is assuming that there is error in the response variable. And when I say error, I mean like measurement error, I mean like variation due to nature and stochasticity and stuff like that. Like there's variation. The regression analysis assumes there is no error on the x-axis. It assumes that when we measure a petal length of, say, 2 here, whatever this value is, that is precisely what it is. And so we're just kind of making you aware of this. If this sound like just trying to put a little nugget in your brain that if it ever matters and you're like doing this kind of research, send us an email, talk to another friendly statistician, because there are models that will allow for error on the x and y axes, which would actually be more appropriate for data like this because there's error in both of these measurements. But we don't want to go into that because that's a lot more complication.
That's statistics 401 at that point.
Yeah, exactly. But it's not that bad. And a friendly statistician could quickly and easily guide you to the right test and talk you through that. So, the number one takeaway, this is new. Brian hasn't taught the Ecolab in a minute, but I think the new biggest takeaway is that when it matters, go consult with a friendly statistician.
Absolutely.
All right.
And when I teach 203, I say the same thing.
All right. That's a consistent takeaway. Okay, let's stop.